See, at first I was telling people, you should take it. I'm like, strongly disagree.
Okay, we're going to continue with finishing up the end of chapter problems in chapter 15. Looks like there's 4 or 5 problems left, and then we'll do review for whatever questions y'all have for the test. So, next question is question 58. So, on the back of the book, it says that SO2, CO2 decomposes to SO2 and CO2, and it gives the K sub C for that, and it gives the initial concentration, and it wants to know what is the equilibrium concentration of one of the products. So, let's see, what's that? Well, it's a little different from the one we just did. So, I'm at least going to go through it where we set up the system of equations. So, let's write out the reaction. SO2, Cl2 decomposes to SO2 plus Cl2, and we know the value of K sub C for that. So K sub C is going to be products over reactants, and everything's a 1 stoichiometry. So maybe good, maybe bad. We want to set our ice up. Okay, so it says initially it contains a reactant. It doesn't say anything about the products, so we're going to assume there's none. So it's 0.0175 molar, and then 0 and 0 for the 2 products. And it wants to know what is the concentration at equilibrium of this guy. Okay. So we need to find out the reaction can only go one direction. It can only go in the forward direction. So we need to find out how far the reaction is going to proceed in the forward direction to reach equilibrium. So since it only can go forward, this is going to be minus x, and plus x, because everything's 1 to 1. So we've got the initial concentration minus x, and x. So now if I plug these into the K sub C expression, right, I've got x times x on top and 0.0175 minus x on bottom, and that's equal to the number of K sub C, whatever K sub C is. So on top, that reduces down to x squared. So like it or not, here comes the math again. So I'm going to take this term and multiply it over to this side and rearrange it in the form of quadratic, which is what it's going to be. So we have, but going back to that, if you were to get it at this stage, I give you half the points. If you set it up and understand it at that stage, you're going to get at least half credit for it. Okay, but we're going for the whole enchilada. We want to get full credit. All right, let's rearrange it. So on the left, I'm going to be left with x squared. On the right, I've got Kc times 0.0175 minus x. So distribute the Kc to both terms. It says that x squared is equal to Kc. And I know what that is, so I'm just going to multiply those out. So it's 2.99 times 10 to the minus 7th times 0.175. So that's 5.23 times 10 to the minus 8th. And then minus 2.99 times 10 to the minus 7th x. Now get everything on one side, put it in the form of a quadratic. The x squared is where we're going to start. It's on the left. I take this term, move it from the left to the right-hand side. It was a negative. Now it's going to be a positive. 2.00 times 10 to the minus 7th x. And this is positive, move to the other side, it's going to be negative 5.23 times 10 to the minus 8 is equal to 0. So now you have a quadratic equation where A is equal to 1, B is equal to 2.99 times 10 to the minus 7th, and C is equal to negative 5.23 times 10 to the minus 8. Okay, you want to solve the quadratic, or do we want to go ahead and do something else? All right, we've done a bunch of those already. So at that point, it's plugging in the equation. You're going to find there's going to be two roots. Only one of them is going to be real. So either one of them is going to come up with a number that's negative, okay, and let's see, I copied that down. Squared. I'm going to write this on the board. X less 0.23 times 10 to the minus 8 x equals 0. Okay, so I just want to show you what we would, the way I would do this in the real world. If this computer still has mathematics on it. How many of you used Mathematica in a class? Okay, a couple of you have. So if you had the Math Tech course or you have calculus, what course did y'all use it in?
Algebra for the science.
Algebra for the sciences. Okay, so that's a where I recommend a lot of students to take instead of college algebra. It has a function called nsolve. So nsolve lets you solve mathematical systems of equations. So you just put nsolve and open up a set of brackets, define my equation, x squared plus, let's see, 2.99 times 10.
Yeah, that's the living right now, works out.
Yeah.
To the minus 7th times x, close the parentheses, minus 5.23 times 10 minus 8. And then you go equals equals, define the inequality, and close the equation, open up a set of brackets to define the variable, which is x, close it, shift enter, and there are my two roots. So instead of, that's the reason I never solve a quadratic by hand anymore, is to use this. As quick as I can type the equation in. One of the values is negative, all right, and it can't be negative because a negative concentration can exist. That's got to be our root, the 2.28 times 10 to the minus 4th, and that's the value of x, which is the chlorine concentration. And that kind of makes small. That's a low number, but the reason that makes sense to me is because this K sub C is very small, it's 10 to the minus 7. It's barely going forward. The equilibrium staying on the side of the reactants. So it's just a little amount of that went forward. So this is the important thing I want you to be able to do, is get it to that point. Now, even if you didn't want to rearrange this equation, so if I didn't want to rearrange that quadratic and get it in the form of a quadratic, I could have just as easily went nsolve bracket and put it in the form that that we first had it as.
Dr. Smith, on the test, like significant figures, do you want us to like do 7.14 times 10 to the second, or do you want us? Is it okay if we just say? Like,
okay, so we need to look at a piece of information like this, either a concentration or K sub C is the limiting factor. So which one's the smallest? So this you got 3 sig figs in both of them, so your answer needs to go 3 sig figs.
Okay.
Yeah.
You'll definitely count on if don't do that.
Well, I want you to do it correctly.
Yeah.
So the way that I do it on sig figs, just to tell you that, is I usually look at a particular problem on a page, and if you miss that problem, I'll put a -1 sig figs, SF. But that's the most you'll lose for sig figs is 1 point. once I count that off on a page, I won't penalize you twice on a page. So it's not going to be a huge. You're going to lose 1 out of 18 possible points. The point's the point.
Yeah.
So I just want you to see that you're making a mistake and you need to correct that mistake. So even if we had it in the form that's listed here, so if I had it in the form of x squared divided by parentheses 0.0175 less x is equal to equals k sub c was 2.99 times 10 to the minus 7th parentheses. Okay, so that's the form of the equation as we wrote it right here. Didn't even have to rearrange it in the form of a quadratic, actually. Well, I entered something wrong. 2.99.
I think you forgot to put the little carrot top.
I did forget the little carrot top. Thank you.
Isn't it 0.01?
No,
Is it?
Never mind.
It is. Those are the same numbers again. So the 2.2 times 10 to the minus 4th. Okay, I just wanted to show you how it's not killer if we can't solve these things exactly, because in the real world, this is the tool that you would use to apply these things to. Okay. All right. So 62 says find the equilibrium pressure for each value of K. Assume that the partial pressure is 1 atmosphere. And partial pressure of B. So this one's kind of tricky in the way it's wording things. So what you're starting with here is you're starting with B at 1 atmosphere, and this guy's at 0. So you've got this guy at 1 atmosphere pressure, and this one's at 0 atmospheres. And it wants to know what is going to be the equilibrium concentrations, and we're going to choose one of them. We'll just do the first one. So K sub P is equal to 1, which is equal to the partial pressure of B squared divided by the partial pressure of A. Okay, so we still need to think about this in terms of the ice. So our reaction a little simpler. I'll write it over here so give ourselves plenty of room. A yields to B, and initial change and what's at equilibrium. We know initially there's not any of A, and we know that B is at 1 atmosphere. Okay, so this reaction has to go in the reverse direction. It's the only possibility, because there's none of A there. So the only thing it can do is go in the reverse direction. So that means it's going to be a minus 2x for this, and an x form for that one. So at equilibrium, I've got x, and I've got 1 atmosphere minus 2x. So I would just plug this into the K sub P expression. So K sub P, which is equal to 1, is equal to what B is, which is 1 minus 2x, but we got to square it over A, which is x, and that's stinking quadratic. So 4x squared minus 4x plus 1, did I expand that right? Over x, and that's equal to 1. Just solve the quadratic. Rearrange the quadratic and solve it. Okay, so all the other ones, the only thing to be different is you'd have a different value for K sub B to put in, but they're all going to involve solving the quadratic in this system. All right. Let's look at a couple of the others. Okay, something different finally. Well, the Chartier's principle. So let's look at each one of these and let's figure out which way the equilibrium is going to shift. Is it going to go the forward direction, reverse direction, or be unchanged with each one of these changes? See all what's going to do with the first one. I add some NO to the reaction mixture. Okay, so if I add some product to it, add the NO. If you add product, the equilibrium shifts back to the left. Okay. B says I add some of the reactant. So if I add some of the reactant to it, what happens to it? Can't go to the left. It's going to have to go in the forward direction, so it's going to go to the right. All right, so what the last one says, in C, is that some of the bromine is removed. So there's a way of removing selectively the bromine gas from the mixture. How's it going to respond? Okay, if you pull a product out, the reaction goes in the forward direction. So when you remove a product, it's going to go in the forward. I promise you, I'm going to give you a question on it. How's it going to respond?
And when it's like asking about this in moles, you don't look at the moles here.
It wouldn't matter if I added 0.1 moles or 10 moles. Yeah, it's still going to respond in the same way. How far it goes is going to depend on KC. But here it just wants to know which way is it going to go. Forward, reverse, or no change are the three options we have to think about. All right. Another similar one. So which way is it going to shift? Forward, reverse, or unchanged in the system. So first thing says the reactant carbon is added. What's it going to do? Change. It's a reactant. Why wouldn't that go forward? It did on the last one. It's a solid. That's the key thing to recognize. As we increase the concentration on this one, it's no change because we recognize that's a solid phase. That's the trick to that problem. All right. So it says water is condensed and removed from the reaction mixture. So the concentration of water is decreased. What's it going to do? It's going to proceed back towards the reactants. All right, carbon monoxide is added to the reaction mixture. So CO is added. That's going to drive it to the left. And H2 is removed from the reaction mixture, the last one. So if H2 is pumped out, that's going to drive it forward. Anytime you remove a product, you drive it in the forward direction. If you add a product, it drives it in the reverse direction. Question on that one? Okay, so on this one, the system comes to equilibrium, then the volume is changed, and some cases it increases, some cases it decreases, and I want to know how it's going to shift. All right, so what happens with A is that the volume is decreased. All right, so if I decrease the volume, how's the system going to respond? What do you say? Okay, which side has the fewest moles? They're the same. So if they're the same number of moles, what happens? No change. Yep. All right, so on the second one, it says the volume's increased. So the volume's increased on this one. So now where's it going to go to? The side with the fewest number of moles or the greatest number of moles? Okay, it's going to go to the side with the greatest number of moles. You've got 1 mole on this side, 2 moles on this side. So it's going to shift in the reverse direction. All right, let's look at the last one. So the last one says the volume is increased. Now what's this one going to do? Okay, so why is it going to go to the right? Okay, so the solids don't count as the moles of gas. I've got 1 mole of gas here, 0 moles of gas on this side. So when you increase the volume, it's going to shift to the side with the most moles of gas. It's going to go to the right. Okay? Question on that? Easy stuff. Okay, we got an equilibrium. This is one of the ways that we would like to basically take coal and take it into an eco-friendly fuel. If we take carbon and convert it into hydrogen gas, right, that conversion, and it doesn't release CO2 in the atmosphere, we could do something with the carbon monoxide maybe, but we could convert it into hydrogen gas, which we could consume, put our energy that way. This is a way of taking the energy out of carbon and putting it in the form of something we can consume that doesn't produce what we think of as classical fossil fuel system. But if this equilibrium is established, so we've got a solid, a gas, and a gas, and a gas, so we want to look at how it responds to these different changes. All right, so the first thing says if I add more carbon to the mixture, what's it going to do? So that's going to be our first one. So add more carbon, increase the amount of carbon. How's it respond? If I dump more carbon in there, what's it going to do? It's a solid, so it doesn't change it. If I add more water to the system, okay, so if I add more water to it, what's that do to it? It's going to drive it forwards. Okay, so I'm adding more of the reactant to it. All right, so we haven't talked about the effect of temperature yet. So if we raise the temperature, this one is it's a trick question. Because depending if the reaction is endothermic or exothermic, we don't know how it's going to respond to a change in temperature. So that can only be, depends on something called delta G, Gibbs free energy. And that's coming up in the next couple of chapters.
Is this endothermic? This is by the endothermic reaction.
Oh, okay, so it's endothermic. So endothermic means it gives energy off or absorbs energy in. Takes energy in. Okay, exothermic gives energy off. So this wants energy. You raise the temperature, you're going to drive it in the forward direction. So we'd have to know that piece of information. I didn't read that. All right, B says increase the volume, or the D says increase the volume. So if I increase the volume, which way does it shift? Okay, so it's going to shift to the side with most moles of gas. I've got 1 mole of gas on the left, 2 on the right. So it's going to shift to the forward direction. Add a catalyst to the system. Add a catalyst doesn't change the status of the equilibrium. Adding an inert gas to the reaction mixture. So I add some helium to it. Nothing. Okay. That's it. That's all the possibilities. So, all right. So that's the end of chapter problems. Do y'all have any test questions you want to look at, or what do y'all want to go over?
Are we going to go homework that we have now?
Which homework? Like the master in chemistry?
Yes.
Yeah, we can do one of those if you want to. I'll give you hints on it. I'll do that, no problem. So, have you looked to make sure there's not a tutorial for it?
For number 6 and 8, I haven't. 13, 14, 15, I have.
Okay, so 6 and 8. All right, that what 6 and 8 are with respect to those. So we'll So this 6 right here.
Yes, sir.
All right, so using plus or minus using equilibrium constants. Make sure there's not one for that. Yeah, I think this is using equilibrium constants. I think that's that one, I'm pretty sure. All right, so we can tell right quick. So what is the equilibrium concentration of D? No, it's a different problem. Okay, so we'll take a look at this one. So it says, I'm going to copy it. Put it on the other board. Okay, so it says you've got initial concentrations of A and B at 2 molar each. What's the final concentration of A once the system reaches equilibrium? And it gives me the expression on the left, and it tells me what the value of K is. Okay, so this is just going to be a problem where you've got to set the ice up. All right, so the reaction is a big pen.
Oh, actually, my bad. I did this part A.
Okay.
Part B, didn't know.
Right. So let's see if we can go down at the bottom and get to the rest of it. It says, what is the concentration of D at equilibrium if A is 1 molar, if the initial concentrations of A and we know what A and B is, still going to work the same way. So we're going to have to set up the ice in the system. So we know the initial concentrations of A is 1 molar and B is 2 molar. So these guys are at 0. So everything's a 1-to-1. So this is going to be a minus X, plus X, plus X. So you've got 1 minus X, 2 minus X, X, and X. So K sub C, which is 3.2, is equal to X squared on top, because I've got C times D, and those are both X. And then, they don't look like X, but they're both X, divided by 1 less X times 2 less X. Stinking quadratic equation, so. Okay. All right, so I'll take you to that point of it. And doing these, if you want to go do that, you can look up how you do that in Mathematica. Mathematica should be on every computer in a computer lab. It's not hard to use Mathematica. It's easy to plug this into Mathematica. Go look at that install the way that I did it on most problems, and you can make it a lot quicker to solve these problems, or you can solve the algebra. It's your choice. All right, so what's the other one you wanted to look at? 6 and 8?
Yes, sir. 6 and 8.
Okay, number 8. Is this one? Is that correct?
Yes, sir.
Right. So it's going to work somewhat similar. Yeah. Copy it over. So this one, the reaction is A yields 2B, and I know the value of K in it. So it's, I know the K for this, but what I want to know is what is the K for this guy. So what's the relationship between those two things? Okay, so if I invert it, all right, so this is, I'm going to call this K, K1. That's our original one. So if I invert it, it's 2B yields A, and now that's value is going to have, inverted, I have to inverse the value of K. But is that still equal to this? What do I need to do? So I need to divide everything by 2. So if I divide everything by 2, that's the same as taking it to the 1/2 power or the square root. So K mu is equal to the square root of the inverse of K1 on that one. Does that make sense? Okay. All right. So is that it for the Mastering Chemistry? Go to exam questions. Okay, look at exam questions then. So, close that up. Content, old exams, 2 or 3? Exam 2. All right, which one?
The first spring,
17, okay. So what problem am I looking at?
number 24.
Number 24. All right, so okay, so I've got a it tells me the combustion of ethylene proceeds forward and gives me a balanced reaction. It tells me the rate of disappearance of O2. So I know something about this guy. Its rate is 0.28, and it wants me to compare that to the rate of the appearance of the CO2. So I need to somehow relate how this one's changing and convert that into the rate of how this one's changing. So the thing that puts the things together is the rate expression. Okay, so the rate for any of these things. So if I write it for a reactant, it's going to be a minus 1/3 the change in concentration of O2 divided by the change in time. And this number is what I know. Okay, so this 0.28 is equal to that ratio. So that's equal to the rate, and for the product, it would be a plus 1/2 times the change in concentration of CO2 divided by change in time. So now I'm trying to find out what is this ratio. So the change in concentration of CO2 as a function of time is equal to, I take the 2 and move it to the other side, a negative 2/3 times 0.28. See if there's a number that looks like choice D. Okay, since this one's disappearing, it's a negative. Negative and negative are going to make a positive. Is 2/3 of 0.28, 0.19? Is D the answer in the key? Okay. So that's the way when you know the rate of one thing, and you're trying to relate that to the rate of something else, regardless of what it is, the relationship is the rate expression. So rate for any reactant can be related to any other reactant or any product by setting them up in that format. So when I tell you the rate of appearance or disappearance, disappearance means it's going to be a negative. Appearance means it's going to be a positive for the change in concentration. That's the thing inside of the parentheses here. Disappearance on the reactant and appearance on the product. Okay. What else?
Number 18 on this again.
Same test?
Yeah.
Okay. No problem.
It's about the orders. I'm just a little confused. I think I'm overthinking.
Okay, so,
Wait, is that the same?
all right, so on this one,
It's
I'm
actually
going to
17.
say again.
It's 17.
Okay. So we can look at 17 and 18, but I don't have to copy these over. Can y'all see that? Is that big enough to see in the room? Okay. All right, it says it wants to know what's the overall order of this rate law. So the overall order is just the product of the orders of both of the reactants. So with respect to NO, it's second order. With respect to the O3, which is ozone, it's first order. So the overall is just the summation of those two. 2 plus 1 is 3. All you have to do is add those together. You know it's third order. Okay? Does that make sense? What?
On the key and the test are different, and there was one missing from, it was number 20 on the actual test. It says which of the following statements is false, and then it gives some about zero order reactions and stuff, and it's not on the key.
If it's not on the key, it's because I didn't grade it.
Oh, okay.
There was something wrong with that question.
Okay.
Yeah. There's a flaw in it. All right, what else?
18.
Same test?
Explain that. Yes, right there.
Okay. So on this one, it's recognizing that this, what is the order of this? If this is the rate expression, rate is equal to, what is it? Second order, because you got first order and first order. It's a second order overall. All you have to do is go to the table and see what the units of K are for a second order.
Do we need to know that?
Do what?
That's not on the test.
Are you gonna have that table?
That table's on the, yeah. So if you look at the equation sheet, the table's there. So all you have to do is go to that equation sheet and find where it's got the integrated rate laws for a zero, first, and second order. Know which one goes to which. And just look at it. So do you have to memorize it? No. So what is it? B, inverse molarity, inverse seconds?
Yeah.
Okay, so that's what it is for a second order. Okay. Right, what's next? Same test?
Yeah, it's the half-life question.
Okay. So it says how many half-lives are required for a concentration to decrease to 25% of its value. I'm just going to go over on this page so I can write. Okay, so if we look at half-life, what's changing? So if we'll think about concentration versus time, and we'll call the original value 1. Okay, it could be any number. So what's changing with the half-life is the time that it takes to get to 0.5. Okay, so this is 0.5 times whatever the concentration original was. All right, if it was 1, it would be 0.5. So that occurs in this period of time in one half-life. It's that period of time. Now the second half-life is the time that it's going to take to go from concentration to cut in half. So go from 0.5 to 0.25, half the original. This would be 0.25. And that takes another half-life. So the question asks how much to go from the original to 25% of the original. The answer is going to be 2 half-lives in the question. So that one is going to take 2 half-lives. Is that a choice? Yeah. Yeah, so choice B.
So with every half-life, it's half what
It
it
was
was just before.
Right, at the previous half-life, yep. So if we would go 3 half-lives, we'd have 1/8. 4 half-lives, we'd have 1/16, etc. 5 half-lives, 1/32. 6 half-lives, 1/64. I can divide the 2 up to a couple hundred. Okay, what else? Different tests.
Exam 3.
Exam 3, same year?
Yeah.
Okay.
Number Number one.
Number 1. All right. So, this one's starting right. Okay, it says find out what the equilibrium constant is for a new one. So what I need to do is take the one that's given that I know its value for. I know K sub C for this expression, and I somehow need to convert it into the other one below. So if I start changing the one that's on top, the first thing I see is that what is a product on this one is a reactant in the one that I want to get to. So first thing I have to do is spin it around. Okay, so if I take the top one and invert it, it becomes 2SO3 yields 2SO2 plus O2. And the value for K for that is going to be the inverse of 1.7 times 10 to the 6th. Okay, now is that where I want to be at? What's different? So is that equivalent to this?
Why did you inverse it and not just make it negative?
Well, I don't know. You can't make one negative. You have to spin it around, you have to invert it.
Oh.
Okay? So the other thing that I have is I've got a 2 here for this reactant, and I want it to be a 1, so I need to divide everything by 2. Divide by 2. Divide by 2, that's going to make that 1/2. That's going to make that 1. It's going to make that 1, 1/2. So I've got 1, 1/2, 1. They're switched around in order, but it's still going to be the same. If I divide something by 1/2, that means I take the square root. So this is just like the problem that we just talked about on the Master in Chemistry. It would be the square root of the inverse of the original case. So, boy, I can't do that in my head. 10 to the third. I'm guessing D, but I don't know.
Yeah, it is.
All right. Back to the test. What else? That's so easy. If you are done, we'll go eat. It's up to y'all. If y'all want to think about it for a couple minutes, we can sit here a couple minutes so you come up with something to ask. This is y'all's time.
How many questions are there?
Every one of them's the same. 25 questions, multiple choice, 6 questions on the end, except for the final exam. We won't even talk about that yet.
On the exam 2 one, there was a lot of them that were just knowledge questions for chapter 14 stuff. So we need to really memorize just instead of, there's not going to be a whole bunch of math stuff for chapter 14, it's just more knowledge.
I'd say do both. You got to be able to do both. It just depends on the mood when I'm writing questions. Something's mathy in my mind, I do a lot of calculations. If I'm thinking memorization stuff, I put more questions like that. So I can't tell you that. If you go back and look at years to years, you see I mix it up. And what I try to be is not predictable. That's my goal on the exam. I want you to know everything. I don't want you to focus in on just knowing a single thing. Okay?
On that self-saving video, we go to
Go to which one?
exam 3 and exam 1.
Problem 10?
Yeah.
Okay. Yeah, we're there.
I don't know what.
Okay, we haven't covered that. That's the next chapter coming up.
Okay.
So, chapter 16, we'll look at acid-base chemistry. On that one, everything from exam questions 1 through 9 are applicable. All the other ones will be on the next test for us.
What test is that? Is that exam 3?
That is exam 3 on spring 17th.
So you said 1 through 9?
Yeah. You want me to tell you where the cuts are on the different exams real quick? Okay. Let's go. Let's do the exam 3s. So I'll go back to 16. So this is exam 3, 16. Looks like through through 12 on that test, on the multiple choice. And it's probably going to be 1 through 3 on our 26 through 28 on the back. All right. Let's go back. I didn't teach it in the spring 15. We'll look at spring 14 right quick. So 1 through 8. All right, let's look at exam 2s. On spring 16, it's 15 through 25. So that's spring 17. Spring 16, exam 2. Uh, 13 through 25. And then spring 14, exam 2. It is 15 through 25. You want to go other years, or is 3 years enough?
On exam 3, the first one, 2017, is 28 hours.
Exam 3, which one?
2017
Okay.
is number 28 hours.
Nope.
Okay.
We haven't talked about POH yet. That's next chapter. But 26 and 27 would be. Okay. Knock that mastery chemistry out, study, and then get some rest. Sleep. Don't try to come in here on 3 hours sleep. Like I said.
Dr. Smith, on the lab, for